Okay, I'm going to talk about network virtualization, not just what it is, but what it's becoming. And the reason I want to talk about this is virtualization in general is something that when you first create it, you normally have something fairly simple you use it for, and then the use cases get very complicated and very interesting, and it goes in a direction that you don't originally imagine. This was certainly the case with compute virtualization. I mean, back in the early days of VMware, compute virtualization was just about server consolidation, really. I remember talking to, so when I was at Stanford, I worked with Mendel Rosenblum, who was the founder of VMware. So he's a good friend of mine. I've done a lot of research with him. And he told me, he's like, well, early on in VMware, we didn't really know, all of the uses of virtualization. All we knew is that you could take two machines and make it one machine, and that seemed to save people money, right? And if you go ahead 10 years now, you've got vMotion and you've got cloud, and I mean, it's become like you've got snapshot and rewind. It's become this general point of indirection. And so, in general, virtualization starts simple and gets very complicated, and we're seeing the same thing with network virtualization. So I've cut my talk into two pieces. First, I just want to provide some background. I don't know how many of you know about network virtualization or what it is, so I want to provide that background. And then I want to talk about how it's being adopted and how it's being used in ways that certainly I never intended, and how I think it's actually changing the way we're thinking about and doing networking. Okay, so let's start at the very beginning. So, network virtualization is one of the most overloaded terms in the industry. Everybody's got a different view of what it means. I'll say network virtualization, and people will say, well, isn't that VLANs or VRF or whatever, right? And so, never mind the term network virtualization. I want to describe exactly what I mean when I talk about it, and that's what I'll focus on. So I'm not trying to define this term network virtualization for the industry, just for the purposes of this talk. Okay, so what network virtualization is. Assume you have a data center, and that data center can have any physical network, anything, right? It could be L2, it could be L3, it could be IP over InfiniBand. Just assume it has unicast connectivity, okay? Connected to that data center, you've got your servers, and for the purpose of this discussion, let's assume those servers are running some hypervisor, whatever. Okay, so within the hypervisors, of course, you're going to have a vSwitch, and so what network virtualization does is it uses all of those vSwitches to create basically a tunnel mesh, which you can think of as a network hypervisor. So, again, physical network, any networking gear you want, all of the vSwitches get worked together to create a tunnel mesh. It creates this abstraction layer, and on top of that get exposed virtual networks. So the idea is that a virtual network looks just like a physical network in that it will support all of the service models of physical networks. It'll support ingress ACLs, L2, L3, egress ACLs, QoS policy, all of the management interfaces, SNMP and NetConf and ERSpan, whatever. It looks exactly like a physical network, but it has the operational model of a VM. It's implemented in software at the edge. You can create it dynamically. You can grow them. You can shrink them. You can snapshot them. You can rewind them. You can move them. So I want to draw a very quick parallel. So I think the most interesting trend in all of networking has nothing to do with VMware, has nothing to do with SDN, it has nothing to do with OpenFlow, it has nothing to do with me. The most interesting trend in networking in the past 10 years is how the mega data centers build their networks. So if you look at Google or Facebook or Amazon or Azure or Tencent or Baidu, these are the most successful data centers on the planet. They're the cheapest to build, they're the most scalable, the operations are they're most operationally efficient, bar none, right? And if you look at these data centers, the networks do almost nothing. In almost every case, the network is an L3 ECMP fabric. That's it. That's it. So the entire network is just passing packets. And then all of the functionality that we often put in the network, things like security, things like load balancing, billing, fault isolation is rewritten as part of the application or the platform. Make sense? So if I'm Google, I control my application. I can write security as part of the application. If I'm Amazon, I control the platform, so I can put things in the vSwitch. If I'm Yahoo, I can do this, right? And so if you look at the most successful, cost-effective, efficient data centers on the planet, the network is just bandwidth and functionalities and software on the edge. Any disagreement? What's great is this has happened over the last 10 years. Nobody sold them this architecture. These are the most sophisticated data center architects on the planet, and that's what they've chosen. They've chosen incredibly simple networks with functionality and software. But the problem is, the only way you can get these advantages is if you own the application, right? The only reason eBay can do this, or Facebook can do this, is they've rewritten the application, or they've changed the web server, or they've changed the load balancer, or in the case of Google, they've changed Linux. I mean, Google will change Linux to solve networking problems. It'll do things like heavy hitter detection. It'll do things like packet pacing, right? So if you own the applications, you can build the world's best data centers. But most IT doesn't, right? Think about, we work with many of the world's largest financial institutions. They run thousands of applications, and they don't control them. SAP, Oracle, SharePoint, whatever. So the point of network virtualization is to use the same architecture, from a high level, an identical architecture to these mega data centers, but in a way that you don't have to change your application, right? So the idea is, build your physical network however you want, L3 ECMP, functionality gets moved into software at the edge, but instead of putting that functionality into an application, we create an abstraction layer that looks just like physical networks. So if you create, you spin up SAP, or you spin up SharePoint, or you spin up whatever, you attach it to what looks like a real network. It still has the counters, it still has L2 service model, it has whatever IP addresses you want to give it. It'll support ACLs, it'll support L3. Support L4 through 7 services. So ultimately, the goal is take existing applications, attach it to virtual networks, but you get the same benefits as a Google-like data center. And again, we know from 10 years of experience that this is the best way to build a data center if you care about CapEx, OpEx, et cetera. By the way, I'm totally happy if you guys have questions while I'm talking, so I'm very happy to answer them. Okay, make sense? Okay, so network virtualization has actually been around for a while. I mean, I think we finished our first version in 2010. We've been in production in some very large environments for 3 years. But over the last 2 or 3 years, the majority of adopters were very aggressive, innovative companies, early adopters, right? So the initial customers were AT&T, Rackspace, eBay, Fidelity Investments, and NTT Com. These were all, building large clouds, internal use cases. But over the last year, adoption has moved from kind of early adopters to more mainstream. And so I just want to talk a little bit about that. So even in just the last 6 months, I've seen network virtualization go from something that only kind of crazy companies use, like really aggressive companies, to most verticals. So 3 of the top 5 financials, Starbucks, Best Buy, manufacturing companies, airline companies. The most aggressive, the most forward-thinking geos are the United States is probably the most advanced, followed by Japan, followed by Australia, New Zealand, probably followed by the UK. And so followed by Brazil is actually a pretty aggressive user as well. So now you're seeing it in many parts of the world and in many different segments. And this is actually relatively recent, the last 6 months. And I actually think the reason we've seen so much adoption is because Cisco announced ACI. I think if you're the only product on the market, people don't know if it's the right thing to buy, right? If they're like, oh, okay, I can build a traditional network, or I can do this network virtualization thing. It's a little bit confusing. But right now, pretty much every major networking vendor is doing network virtualization. I mean, if you look at like ACI. It's network virtualization. It's an overlay under the covers. It's like the problem that VMware is talking about, that's the right problem to solve. It's about operations. It's about creating virtual networks, blah, 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 blah. It's just the architecture is a little bit different. And so now the customer choice isn't like, do I do network virtualization or not? It's not that question anymore. It's like, which one do I do? And I actually think most new networking approaches look like this. It's not just a VMware thing, right? Microsoft is doing this, Cisco is doing this, Juniper is doing this, Alcatel-Lucent's doing this. And this is kind of the way to do networking. And like, virtualization is really powerful, right? It's that point of indirection that we use in computer science to do cool stuff. So I think we're going to see a lot more of this. Okay, one last validation for the maturation of the market. This just happened. I know you can't read this slide, so I'll tell you what it is. So just, I think in the last week, Gartner put out their Magic Quadrant and put VMware as the most visionary for networking. So there's two things that are very interesting about this. VMware's not a networking company, traditionally, ever. We've never been on this quadrant before, ever. And we're most visionary. This is us right here. And the second thing is we're the only software company up there. This is a quadrant for hardware players. This is for like Cisco and Ericsson and Juniper, right? So this is, I mean, to me, this blows my mind. Gartner is generally somewhat of a laggard, right? I mean, as far as these trends. And so we're starting to see customer adoption of network virtualization, but also the analysts coming around. So let me talk about kind of the basic use cases, like why do people buy and use network virtualization? I'm trying to provide the context now, then I'm going to go into a technical deep dive next. So I just want you guys to understand why this is catching on and how much it's catching on. Okay, so the original use case was just provisioning time. It's really simple. So if you're trying to do something and configuring or provisioning the network takes time, and that's causing you pain, network virtualization will reduce that to 0, right? So a classic example is eBay. They had a developer cloud, spinning up a VM, 30 seconds, doing the network configuration, 49 days. You take that to 0, they develop faster, right? And so all of the original customers were trying to like make business factor by reducing network provisioning time. So there's not that, that's only a subset of the market, right? There are many customers like, listen, I use VLANs, I have a small operation, I don't need to change things, I don't need network virtualization, right? This was a very specific use case. And normally it was, if deploying an application took a long time, or onboarding a customer took a long time, or perhaps onboarding a new employee took a long time, then there was value. So that was all of the early deployments. A secondary reason was just cost, which it turns out if you decouple the service model from the hardware, you can buy cheaper hardware. What's interesting is often you buy it from the same vendor. You just buy the simpler version of it, right? So this wasn't nearly as much of a driver as provisioning speed, but some of the early deployments were trying to save cost. What's interesting, and I'll talk more about this, is now about 40% of all network virtualization sales are because of security. And I'll deep dive on why this is the case, but I actually think this is probably going to be the #1 use case in the next couple of years. You can actually build much, much more secure data centers by using network virtualization. So I'm not going to talk about it now. I'll talk about it a little bit later, but I just wanted to let you know that, again, 40% of the sales in the last 6 months about security. So any questions on use cases? These are the use cases that drive, there's probably hundreds of network virtualization deployments today, and these 3 drive almost all of them. That's why people, okay? All right. Okay. All right, so that was the basics. That's kind of here's network virtualization very quickly, here's why people use it, blah, blah, blah. I've probably given that talk 50 times. But now I want to talk about, okay, so you have this thing and people are using it, like, how are they using it in ways that we didn't envision or are interesting or are creative? So let me talk a little bit about visibility and debugging. in general, when you decouple software from hardware, you can do really cool stuff with debugging and management. I mean, I'm guessing a lot of you guys are kind of end system guys, right? So I used to work at a national lab. We used to build our own compilers. We'd build our own operating systems because we worked on these weird architectures. And like it was very difficult if you just had a bare metal hardware to do real program debugging because you didn't have a symbol table. You couldn't manage all of the program memory in the same spot. So until you had things like virtual memory abstractions, real processes, it was very difficult to debug. But as soon as you have a process abstraction, the ability to introspect it with things like ptrace, you actually have virtual memory, you can build really interesting tools like GDB, like debuggers. So I think the same thing is going to happen in network virtualization, which today, to me, debugging a network is crazy. It's like debugging a mainframe in the 1960s, right? You're dealing with hardware addresses. Those hardware addresses change because they get remapped. You have no symbol information. You have no context information. Let me give you an example. So here's state of the art. Let's imagine you get a packet trace in your network, somewhere in your network, anywhere. So you take that packet trace and you put it in the closet. And then 3 months later, you come back and you look at that packet trace. What does it tell you? Nothing. It tells you nothing, right? You don't know what the network topology looked like when that was captured. You don't even know if those IP addresses are still bound to the same machines. You don't know what configuration was on the network. It tells you nothing. Maybe there's some communication going on, right? It's unbelievably bad computer science, the way that we debug networks today. It's horrible. We should be embarrassed as systems people, right? What do you want to know? If I take a packet trace file from the closet that I captured a month ago and I look at it, I want to know everything. I want to know the user. I want to know when they sent it. I want to know what the network looked like. I want to know who they sent it to. I want to know all of the ACLs. I want to know all of the configuration. Because without that, I can't reconstruct a damn thing. Right? But in networking, we've never been able to reconstruct this because we don't have global state. Networking is just distributed state managed by human beings. And human beings suck at distributed state management. They're horrible, right? We're lazy. We get hungover. We're malicious. I mean, you know, to manage all of this state and construct a view is impossible with humans. But with network virtualization, you have to. You have no choice. You have these global views and these global abstractions, and you can use that to reconstruct everything. So let me talk about that very quickly. Okay, so the basic idea is this. Today, networks are complex because you've got all of this distributed state. You know, you've got VLANs and VRFs and ACLs. You don't know where packets are. IP addresses are being reassigned. There's no notion of space or time. With network virtualization, I actually have an abstraction that's meaningful. I'll give you a virtual network. That virtual network will have traffic on it, and I have to build a network virtualization solution, I have to track every state change of that virtual network. I have to. Because that's how you build these things. It's just like a process for a server. Which means if you collect, so in a virtual network world, you're like, I am interested in virtual network 3. And I can tell you not only what it looks like today, but I can tell you what it looked like 3 days ago. I can tell you the configuration that was on it. And you don't, you know, these things aren't subject to things like source spoofing or IP spoofing, right? Like we know from like where in RAM the packet came from, everything. And we attach and annotate all those packets. So you've got all of this rich information to build kind of different types of debugging tools. I want to give you one example. So this is actually a screenshot from an internal production cloud. It's actually an OpenStack cloud that we use internally. So one of our big early customers was Rackspace. It still is. I mean, it's the largest hosting provider in the world, second largest cloud in the world, probably 100,000 VMs. And never mind this. So before network virtualization, here's how they would determine if there was a problem. Are you ready? The phone would ring. That was it. And someone was pissed off. That's how you determine there's a problem in a complex network. And the reason is there's no way to monitor all of the stuff that's going on. So unless someone's irritated and calling you or not paying their bill, you don't know there's a problem. Again, this is ludicrous, right? I mean, we're systems guys. So this is actually a modified version of VC Ops that is mapped into NSX to provide a global view. So this picture here, this is every virtual network that's monitored in real time. So every dot is a virtual network. I don't remember, I think maybe we have 2,000 virtual networks in our internal cloud. So for every virtual network, we track something like 23 different characteristics. You know, latency, packet drops, end-host resource usage, blah, blah, blah. And you also know the virtual topology of that virtual network. I've got a load balancer, I have a firewall, it's L2, it's L3, here are the VMs attached to it. But more importantly, you can look at the entire set of all virtual networks and determine if things are going bad, right? So if the dot is red, there's a connectivity problem, and if the dot is white, there's some threshold that's been crossed. So the reason we can do this is because in order to do network virtualization, you actually have to maintain that much state. For those of you that know operating systems or are developers, it's just like building an MMU. It's just like building a big virtual memory manager. You have to map from physical addresses to virtual addresses globally. So we have to monitor this information anyway, so I can reconstruct things globally. So not only that, so you get a virtual view, you know if things are bad, because you have to actively monitor these things, but you can also map down to the physical and back up to the virtual. Right? So you're like, oh, let's assume, I don't know, let's assume, you know, this guy's having a connectivity problem. Because we have to maintain all of the mappings between virtual and physical, we can be like, okay, well, you know, this guy is sitting on this physical server, which is maybe the CPU is pegged, or maybe it's taking this physical path in the network, which has some latency issues. And you could do it the opposite. If you're like, wow, I know that I'm looking at this, by the way, is the physical. This is like a heat map of the physical network. This is all paths in the physical network, and if there's latency or delays. So you're like, oh, wow, I know that over here I'm having some congestion. You can determine which VMs are being affected by that. I mean, again, this is like, from a networking standpoint, this stuff is super sophisticated because you haven't had these tools. You haven't had anything that maintained this much state before. Okay? All right. That's just a point on, so I think we're actually just starting with visibility and debugging. I think as we go in the future, it's going to become a lot more sophisticated, but this is just a start. So another thing is cool is snapshot cloning and modeling. So again, we have these abstractions, which are these virtual networks, and we have to maintain them anyways. So there's no reason we can't treat them like a VM, like a file. Like I snapshot it, I can rewind it in time, I can clone it, I can move it. So I just want to give you one example of this being used in practice. So this is actually used in production. So some of our early customers are very big, right? We've got a customer, almost 100,000 VMs, tens of thousands of virtual networks. And when we release a software upgrade, you know, we're in real time upgrading, you know, thousands of hypervisors. And because all of the configurations are very different, especially for early versions of the software, we wanted to make sure we didn't screw something up. And so, and we actually hadn't anticipated doing this, but so what we've done is we've had the ability now to go to an existing environment, snapshot the entire environment, clone it, move it locally, reproduce the entire thing. We're talking tens of thousands of networks. So snapshot, clone it, bring it locally, and then test all the upgrades locally to see if it works. If it works, then we test it on site, if that makes sense. It's kind of interesting. I've actually seen customers use this internally, for example, to move an application between dev, staging, and production. Like, they'll try something out in dev. If that works, they'll move it to staging. If that works, they move it to production. Again, this doesn't require changing ACLs or changing configuration. It's just like moving a VM, like moving a file. But this is the entire network configuration. Yeah? Exactly. Yeah, everything but soft state. So you're like, I have an application. It's connected to an L3 router with a firewall, and it's got a certain IP state. You snapshot the entire thing, and you can move that. So all of the ACLs, all of the QoS policy, everything, all of the forwarding state, everything. But again, you have a virtual network abstraction. You have all of that state. You might as well treat it like a file. Okay. This one's a little geeky, but it's kind of cool. So a cool thing about virtualization in general is you get to decouple correctness from performance. Does that make sense? Like, something can work and be correct, but be really slow, and then you can make it faster without changing that correctness. And networking is not like that. Networking, for example, if you have one load balancer, adding another load balancer normally requires a change in configuration or something. I mean, it's actually visible from that view. It's difficult to add performance in networking unless you've got a very special configuration. But in network virtualization, I give you an L2, L3 router, and then I can improve my implementation, and then it should just be faster. I mean, this happened in compute virtualization, right? Early versions of compute virtualization, they had some performance glitches. However, the abstraction of a virtual machine didn't change, but the performance got way faster. As hardware got faster, as hardware support got implemented. So it's cool. You don't have to change your VM. Things get faster. The same thing happens with network virtualization. So I want to talk about a specific example of this. So in something like NSX, you can create a virtual router, right? So let's say I want to do Hadoop. And Hadoop with 10,000 VMs, which would be too big for an L2 segment. So I want to connect it to a very big 10,000 port virtual router. So depending how you implement that router, if you implemented it poorly, it could be centralized. So in early versions of NSX, this is not the case now, but in early versions of NSX, we actually centralized the implementation of these things. So they were limited in scale. So they worked correctly, but they were limited in scale. And so in later versions, we distributed the routing so every server implemented a little bit of routing. So now if I give you a virtual router and it's on 10,000 VMs connected to 10 gig ports, you get 10,000 times 10 gig ports of switching capacity. So if you distribute it, you get full line rate and as much switching capacity as possible. So from early versions to later versions, we went from a centralized kind of bad implementation to a distributed good implementation. But the important thing is, like, we were upgrading production networks in a way that you didn't have to change anything. So I actually got an active latency trace. This is from a production. This is a production customer. I think these guys were running like 20,000 virtual machines. So this is bad and this is good. So this is high latency. So these are pings. This is high latency over here. So before the upgrade, all of the traffic was going through this centralized router implementation. We upgrade it, we distribute it, and then the latency dropped away. So the point isn't that the performance is good. Like now, network virtualization solutions, the performance is awesome. It's almost always line rate. But the point is like it allows you to change the properties of the system without changing the application, without reconfiguring anything. This is like a software upgrade. I mean, listen, I don't know if this is true. This is probably a lie. But like, I think that we've done the largest network upgrade ever in the history of humanity in under an hour, right? So normally when you upgrade routers, the software on routers to new functions, you've got to like move traffic off of it and take it down or take everything down and have I mean, it's very difficult to do upgrades. I mean, these things happen in a matter of seconds, right? Without changing anything. Okay, this one's also kind of geeky, but it's one that I really like. So one of the coolest things about network virtualization is that it's implemented in the vSwitch. And that means that it's very close to the applications. It's actually co-resident. This is something networking has never had. Networking has never actually known what's going on in the end host ever. We've always guessed, right? We're like, oh, I think this IP address means this. So like, networking has never really had visibility into what's going on. And we're just starting to realize how powerful that is. Like, I think this will, honestly, I think this will change networking just because we're so close to where the application is. I'm going to give 2 examples of why that's the case. But you have to remember, networking has always had to guess what's going on, right? You have packet headers, they mean almost nothing. But if you're co-resident, if you're sitting there on the server, I can look in memory, I can look in RAM, I can look at what's going on, and I can optimize myself as a result. And this solves like problems that have been outstanding in networking for years. So the elephant and mice problem is a classic problem in data center networking. It's been around for 20 years. And I think with network virtualization, we can solve it trivially. Let me describe the elephant and mice problem. OK, so here's the elephant and mice problem. So in a data center, the vast majority of flows are really small. In a typical data center, 80% of flows are 10 packets or less. We call these mice. So they're normally latency sensitive, like say part of a database query or maybe part of a web query or something like that. So mice, latency sensitive and small, and the majority of flows. So while 80% of the flows, or the majority of the flows are small, the majority of packets tend to be in long flows. We call those elephants. So this assume you're moving a VM, or you're doing a backup, or something like that. So these flows are not latency sensitive, they're throughput sensitive. They want to get as much data across in that time. These are elephants. So here's the elephants and mice problem. I think I probably have it written down here. Here's the elephants and mice problem. Classic problem in data center networking. If you have multiple elephants hashed to the same link, you will fill up all of the queues into that link. Then all of the mice will have queuing delays, and your latency-sensitive mice now will start getting dropped. You have TCP synchronization issues, and you have performance problems. This happens in every major data center I've ever worked at. Big flows, fill up queues. Small flows, pay queuing delays. Huge problem. So it's actually really easy to solve this problem if you know what a big flow is and what a small flow is. It's really easy. If I know what's an elephant and I know what's a mouse, it's very easy for me to solve this problem. I can put them in different queues. I'd be like, here, this is an elephant, Q1, this is a mouse, Q2. You can take elephants and you can chop them up and turn them into mice, and then do reordering on the Ingress side. So there's many ways to solve this problem, but you have to detect elephants. And nobody knows how to detect elephants. You can't do it in the network because it reduces the flow tracking. You know, you'd have to like track every flow. Normally, by the time you detected it, it's gone. We've been attempting this in networking for years. So here's the cool thing about doing network virtualization. Actually, ignore that. Just listen to me right now. So here's the cool thing. Because network virtualization is implemented in the vSwitch, you actually can predict the future by looking directly into the TCP send buffer, right? I don't have to guess. I don't have to track anything. I can just be like, here's a TCP bound socket. The buffer is this big. We all know how TCP works. It's going to send this much data. That's an elephant. So, I mean, this is like, make sense? Right? I mean, it's there. Like, so if you were doing it from within the network, you've got to do some stupid stochastic approach. You'd have to like try and count every packet, and you'd have to track every flow. Impossible. We've never been able to do it, ever. This is 20 years of trying to do this in hardware. Impossible. But if you're already in the vSwitch, you just look. You're like, damn it, you know, I've got a gig of, you know, I did a system call on send file, or here's the TCP send buffer. You predict the future. You know, you mark it as an elephant. So we're actually doing this today. It's unbelievable. We're like, these big data centers in production that have had this problem, we're just like, yeah, that's an elephant. Put it, you know, mark it with a DSCP bit and put it in a different queue. Make sense? You guys should be blown away because that's so awesome. Okay. Okay, so I'm going to finish up just talking about security very quickly, and then I'm done. Okay, so so one of the base use cases of network virtualization is security, and the simplest way to think about it is that with network virtualization, you reduce the attack surface by a lot. So what do I mean by that? So I used to work for the intelligence agencies in the United States. So before I did my PhD, I worked doing computer security with the government. And in a data center, there's very little security behind the perimeter. It's just too difficult to put security there, right? We put almost all of the security on the perimeter. 80% of our security spend is on the perimeter. But within the data center, where all of the applications are and all of the data is, there's very few security controls. I mean, you can't put a firewall on every server, right? You'd have to like hairpin traffic or something. It's too difficult. So actually, and like I always assume a server can be compromised, right? I always assume you can break into one server. I mean, when I worked in the intelligence agency, we had spreadsheets that would list how much money it would cost to buy off people in certain countries, right? So like you can always get code somewhere if you really want to. And the problem is once you compromise a server, it's actually pretty easy. Imagine I compromise a server in a data center. What can I attack? Well, I've got the top of rack switch. There's probably 7 million lines of iOS code. I've got shared DNS. I've got shared DHCP. I've got shared AD. I've got a shared ARP cache that I can exploit with gratuitous ARP. I probably got dynamic VLAN trunking protocols. I can address every physical server. It's like unfettered access to everything. I mean, if you look at the recent RSA, there was an attack in RSA, which was, they'd gotten behind the perimeter, they exploited one of the servers, and they pretty much took out all of the interesting information from a security company RSA, because it's too difficult to put security controls in the data center. It's too difficult to actually put the security controls here because you require too many boxes. So what network virtualization does is it actually reduces the attack aperture to just a virtual network. So if I spin up a VM and I don't put it on a virtual network, I ping sweep, I see everything. If I put it on a virtual network, I ping sweep, I see nothing. It's that simple. So then if I compromise, if an application gets compromised, it's localized. You can compromise the other VMs on that virtual network, maybe its own version of a firewall, but nothing else. The physical network isn't in the attack surface. The middle boxes aren't in the attack surface. It's a very localized compromise. Make sense? And so this is driving a lot of the adoption of network virtualization. The big financials are like, listen, every application will be on its own virtual network. It'll have its own firewall, its own load balancer, its own IDS. And you know what? If it gets compromised, at least it's not compromising everything else. It's localized. Make sense? Yeah. Bye. OK, cool. All right, in the last 5 minutes, I'm going to talk very quickly about the future and security, and then I'm done. Forget the term Goldilocks. I thought everybody had Goldilocks it's a child's story that it seems is only in the United States. So this doesn't localize. Okay, very quickly. So I think we can do even better in security. And let me describe how. So generally today in security, we put security controls in one of two places. We'll put security in the end host. If you put a security control in the end host, you've got a lot of information, right? You have users, you have files. I mean, you know everything. You know the application, you know the usage. So you've got great information, but you have no isolation. So if the application gets compromised, you're screwed because it can just turn off your security control, right? So if you put security controls in the application, you're great for information, but you have no isolation. If you put security controls in the hardware, which is the other place we put it in the infrastructure, you have the opposite problem. So if I put a router ACL, you've got good isolation. If the application gets compromised, you're OK. It's not going to turn off the ACL. But the problem is you have no information, right? You don't know anything. You don't know users. You don't know application. You know nothing. And so security has always been this way. You either have great information, no isolation, or great isolation and no information. So one thing that we've been working on is using the hypervisor to give you both. Give you both deep visibility into the application, but real isolation. Again, this is something that we've never really been able to do in security, not to my knowledge. So let me tell you a little bit how that works. So I'm actually just going to go ahead and end on this slide, but I want to give you a glimpse in how this works. This is actually technically a very difficult thing to do. So basically, in order for the hypervisor to see into the guest operating system, you need to have a presence in the guest. You can't do it from the hypervisor because the guest is a black box. So basically, you have to install something in the guest operating system that has access to everything, that can see everything, but you have to protect it from the hypervisor. So the hypervisor has to protect the integrity of that in memory and make sure that when information gets passed down, that's secure. So this is maybe a year's worth of working on ESX to figure out how to do that. But now we've got to the point that I can run something in the guest that has visibility to anything the guest has. I know applications, I know users, I know what files, what objects are, I know everything. And I can get that information in a way that can't be turned off because it's the hypervisor that provides it. And I can pass that information down to the hypervisor to be used for security controls. So for example, I can do firewalling over users. Or if I want to do vulnerability assessment, and instead of like scanning remotely and trying to figure out what's going on, I can look directly at the files. I can do antivirus remotely. So the antivirus is running remotely and is looking directly in. So this allows you to actually build security controls and products that have the visibility and the isolation. Again, something we've not traditionally been able to do, but you can if you take advantage of the position of the hypervisor and how close it is to the application. So I'm running out of time. I had a few more slides on this, but I'm just going to go ahead and end them up. But like the bottom line is I do think that the hypervisor is in the position to do both context and isolation. And we're going to be spending a lot of time going forward, at least I am, on how we can change security products to take advantage of that. So with that, I am happy to open it up to any questions you guys might have. Any? No? No? All right. So clear? It's my hand gestures? All right. Okay, well, hey, guys, thanks very much. I appreciate you guys taking the time.